Okay, here we go. We're going to work on lesson 28, which is in your textbook, starts on page 155. So I'm on lesson 28. Pen. There we go. Lesson 28 in calculus. All right. Okay, we're going to learn how to graph these polynomials. Now this polynomial is already factored for you, which makes it a lot easier. You know how to factor these x to the fourths and now, but this one's already factored for us. So we're going to look at this and we see it's a fraction. All right, what makes a fraction 0? What makes a fraction equal to 0? Well, when the numerator equals 0. Okay, for what values make this numerator 0? 0 and 7. All right, what makes a fraction not exist? What gives us a vertical asymptote? We're going to call our vertical asymptotes poles. Okay, for what values of x do I have a pole? Well, I'll have a pole when x equals -5, x equals -2, x equals 2, and x equals 5. Okay, so that's the first thing we have to know. Where are my zeros and where are my poles? Now, the next thing we're going to worry about is what is the limit as x approaches infinity? All right, what is the limit as x approaches infinity? At this point, you're wishing it wasn't multiplied out, right? It wasn't factored out, because you know how to take the limits of those polynomials when they're not factored. So let's unfactor it the easy way. See this negative sign, this pesky negative sign? Let's bring it up here into the numerator. So this is going to be negative x squared plus 7x in the numerator divided by 1, 2, 3, 4 x to the fourth plus some number times x cubed plus some number times x squared plus ... Okay, why do I not care what those coefficients of x cubed and x squared are? What's our rule for finding the limit as x approaches infinity? We look at the denominator. So as I'm going to do this as x approaches infinity, then that's just going to be -1 over x squared plus 7 over x cubed divided by 1 plus some number over x plus another coefficient divided by x squared plus ... Now we don't care what those numbers are, because when I'm taking the limit as x approaches infinity, this is going to be -1 over 0, otherwise known as 0 from the negative side, right? Divided by 1 plus 0 plus 0 plus 0. Okay, so it's going to be 0 from the negative side. Now turn around and look at the other one. What's the limit as x approaches negative infinity? The limit as x approaches negative infinity, what changes? Nothing, because see, x is squared here. So again, it's going to be the negative side of 0 over 1. So as x goes to infinity and x goes to negative infinity, on both of those cases, I'm going to 0 from the negative side. All right, so let's call up our Cartesian plane here and let's graph this. All right, when we go to graph this, first thing I'm going to do is graph my zeros. What color? Let's graph in pink, maybe. All right, let's graph my zeros. 0 occurs at 0 and at 7. 1, 2, 3, 4, 5, 6, 7. Ooh. At 0 and at 7. All right, my poles occur at -5. 1, 2, 3, 4, 5. That means I come over to -5 and I draw a vertical asymptote. That's supposed to be vertical. All right, at -2, I draw another vertical asymptote. At +2, I have a vertical asymptote. And at +5, 1, 2, 3, 4, 5, I have a vertical asymptote. All right, those are the places where I know my function doesn't exist. Why does my function not exist? Because my denominator is 0. All right, so now let's graph this. As I go to infinity, I'm headed over here towards positive infinity. I'm approaching 0 from the negative side. So I come up here and I'm approaching 0 from the negative side. Well, somewhere down here, and we'll use different methods to find where, we're going to turn around and go through our 0. And then we're going to approach our asymptote. Now look at my asymptote. That That occurs because in the denominator I have x minus 5. This is not x minus 5 squared, so my sign's going to change. I'm going to flip signs and I'm going to start approaching negative infinity down this way. Now, as I approach this asymptote, I can't cross it. I can't cross the x-axis because I don't have another 0. I'm going to turn around and come back. Hit this asymptote, flip signs. Nothing's squared, so I have to flip signs. Now this 0, I'm going to cross through that 0 down to this asymptote. Again, flip signs. I have to come back up here. No 0, I have to turn back around. It's like an awful lot like secants and cosecants and a tangent stuck together. Now I'm going to flip signs again and then approach negative 0, 0 from the negative side. All right, and that's how you would graph this one. All right, so that's example problem 1 in lesson 28. So let's get rid of this one. Problem 1, let's get rid of the Cartesian plane. And let's go with problem 2. All right, problem 2 doesn't have that pesky negative sign in front, but it does have something different. Now, if I were to ask you what are your zeros and what are your poles, you might run into a problem here. Because you see positive 1, it can't be both. It can't be both a 0 and a pole. So we have a third category that's called a hole. All right, the 1, since it can't be both a 0 and a pole, we're going to call that our hole. The function doesn't exist there, but it carries on as if it did. All right, my zeros are going to occur at negative 5, positive 3, and my poles are going to occur at 4, negative 2, negative 4, and there's my hole at x equals 1. All right, I forgot to tell you, this is example problem 2 on page 158. Example problem 2 on page 158. Now I could go through the same thing here, and I would see that this numerator would be x cubed plus dot dot dot, and my denominator is going to be x to the 4th plus dot dot dot. Okay, well the limit as x approaches infinity of this one turns out to be 0 over 1. 0 over 1, so as x approaches infinity, that's going to be positive 0. And as x approaches negative infinity, that's going to be a negative 0 over 1. So we're going to approach 0 from the negative side. X cubed, negative is going to put a negative value up here, but again, it's going to be very small negative value, so it's going to be approaching 0 from the negative side. All right, so let's call up our Cartesian plane. If I can get that to come back up there. All right, and we're going to graph this one. Now I have this issue. What do I do? Well, first of all, let's put our zeros. All right, our zeros, change colors. Our zeros occur at negative 5, 1, 2, 3, 4, 5. Negative 5, positive 3, 1, 2, 3. Our poles occur at 4, 1, 2, 3, 4. Right there. Negative 2. Oops. There we go. That's better. Negative 2 and negative 4. Yikes, that negative 5 is like right on top of it. Okay. Negative 4. Okay. So far so good. There's our poles. There's our zeros. What do I do about this hole? Well, I like to go through, I don't think your textbook does this, I like to go through and find out what's my approximate value at 1. So let's just pretend these guys don't exist, and let's put in a 1. And that's going to give me 6 times negative 2, so negative 12, divided by negative 3 times 3 times 5. Okay, so negative 12 divided by negative 45. Okay, so it's going to be a positive around a quarter, right? So 12 over 48 would be 1/4. So it's going to be positive value right around 1/4. So when x equals 1, right here, I'm going to be positive and my hole is going to be right there. Okay, so there's my hole. When x equals 1, that's my hole. All right, so let's start plotting this. As I approach infinity, again, let me change colors. So you can see it. As I approach infinity, I'm approaching 0 from the positive side. Head towards that asymptote. Turn around. Come back through here. Go up through that 0. Hit my hole. Pick up my pen. Go to the other side. Go back up towards that asymptote. Okay. Flip signs. Come down here. Back around. Flip signs. I have to go through the 0 somewhere in here. I'm going to turn around and go back and approach 0 from the negative side. Okay, again, all of this is in your advanced math book towards the end of the book. So I recommend, if you did not take third semester advanced math, you go in and review this just a little bit more. Okay, so let's get rid of problem 2 and finally call up some calculus here. Okay, and we'll get rid of the Cartesian plane. Also turn that off and call up problem 3. Okay, special limits. Okay, we've already learned these. What is the limit of 1 over as x approaches 0? Oh, stop that. You always do this to me. Okay. Not that one. Call that up. All right. What is the limit as x approaches 0 of 1 over x? Well, we already know that does not exist. The limit as x approaches 0 of 1 over x does not exist, right? Because, remember, it looks like this. So as I approach 0 from the left, it's positive infinity. Approach 0 from the 0 from the left is negative infinity. 0 from the right is positive infinity. So the limit as x approaches 0 does not exist. But 1 over x squared, that, however, for coming up here and up here, we call that positive infinity. All right, so we've learned those two. The other one we've learned is this one. You would factor out of 4, so you would get x plus 2 divided by x plus 2. Whoops. As I approach 0, it doesn't matter. That's going to be 8 over 2. It's going to be 4. All right. As x approaches 0, I can just plug in a 0. My value exists. Don't do that part. My value exists. 0 plus 8 over 0 plus 2. It equals 4. And now finally here, oops, I believe this is supposed to be the limit as x approaches 3. Yeah, it is. The limit as x approaches 3, I can't put it in this because that makes my denominator 0, so I have to have some technique. So I'm going to factor my numerator, x plus 3 times x minus 3 divided by x minus 3. Aha, that's what we call a whole, right? So there's my whole, leaving me with x plus 3. As I put in 3, this one's going to approach 6. All right, so those are limits we've already learned how to do. Now we're going to have some special limits. All right, where'd my pen go? Okay, so let's turn off problem 3, I hope, and call up problem 4. All right, this is special. All right, what is this? This is the definition of the derivative. The limit as h approaches 0 of x plus h minus sine x over h. All right, so the limit, this is the definition of the derivative of the sine, which we know is the cosine, right? That's the cosine. The derivative of the sine is the cosine. So, problem 4. What happens when I make x equal pi over 2? Okay, this is written then as the limit as h approaches 0 of the sine of pi over 2 plus h minus the sine of pi over 2 divided by h. Well, again, this is the definition of the derivative. So this is the derivative of the sine. This is the derivative of the sine of x when x equals pi over 2. So what's the derivative of the sine? The cosine. And what's the cosine of pi over 2? Pi over 2 is 90 degrees. Cosine is the x, so that's 0. All right. So all of these special limits, if you look in the bottom of page 158, you're going to see the limit as h approaches 0 of e to the 3 plus h minus e cubed over h. Well, that's the definition of the derivative. That's just simply the derivative with respect to x of e to the x when x equals 3. Well, what's the derivative of e to the x? E to the x. When x equals 3, that answer is e cubed. All right, so these special limits are ones that we're supposed to recognize. We're supposed to see that and recognize that that's the definition of the derivative. Okay, hopefully this will work. Bye.